Hello student, good morning. I am Dr. Kumar Sinha, Professor of Chemistry. Today I am going to discuss chemical properties of group 17 elements, means halogen. Last class I have discussed introduction and oxidation state of halogen. Now I am going to discuss chemical properties. In that I have already discussed oxidation states. Now other reaction I am going to discuss. All the halogens are highly reactive. They react with metals and non-metals to form halides. The reactivity of the halogen decreases down the group. The ready acceptance of an electron is the reason for the strong oxidizing nature of halogen. The ready acceptance means quick acceptance of an electron is the reason for the strong oxidizing nature of halogen. F2 is the strongest oxidizing halogen and it oxidizes other halide ions in solution or even in the solid phase. In general, a halogen oxides halide. A halogen oxidizes halide ions of higher atomic number. A halogen oxidizes halide ions of higher atomic number. Reaction you can understand like that: F2 plus 2X minus. X means halide ion. F2 plus 2X minus, just like Cl minus, Br minus, I minus. Then F2 plus 2X minus, it means it will give 2F minus plus X2. 2F minus plus X2, where X is equal to Cl, chloride ion, bromide ion, iodide ion. Okay. Next reaction, Cl2 plus 2X minus. It will give 2Cl minus plus X2, where X is equal to bromine or iodine. Br2 plus 2I minus. It will give 2Br minus plus I2. The decreasing oxidizing ability of the halogens in aqueous solution down the group is evident from their standard electrode potential, which are dependent on parameters that I will tell now. As for example, half X2, X is halogen, half X2, it will convert into the gas. Half X2, it will dissociate and it will convert to gaseous phase X, and X will convert to this ion X minus ion in gaseous form, and after that this gaseous ion it will dissolve in water and it will form X minus aqueous. This I told reaction takes place in water. Half X2 will convert into X, means a gaseous phase X, and X will convert to X minus ion in gaseous phase, and this X minus ion will convert to X minus in aqueous, means water. Okay, and here you can say heat of hydrogen, it will release heat that is called heat of hydration. The relative oxidizing power of halogen can further be illustrated by their reaction with water. Fluorine oxidizes water. Fluorine oxidizes water to oxygen, whereas chlorine and bromine react with water to form corresponding hydrohalic and hypohalous acid. Again, I am telling you that fluorine oxidizes water to give oxygen. Fluorine oxidizes water to give oxygen, whereas chlorine and bromine react with water to form corresponding hydrohalic and hydrohalous acid. Two types of acid: hydrohalic acid and hypohalous acid. The reaction of iodine with water is non-spontaneous, means it will not react so easily. Non-spontaneous. In fact, iodide ion can be oxidized by oxygen in acidic medium. In fact, iodide ion can be oxidized by oxygen in acidic medium. Just the reverse of the reaction observed with fluorine, reverse of fluorine. Reaction you can understand like that: 2F2, fluorine is gas, you know, 2F2 plus 2H2O. It is reacting with water, 2F2 plus 2H2O. It gives 3 product, 4H plus 4F1 minus fluoride ion plus oxygen gas. 2F2 plus 2H2O, it gives 3 product. 4H plus means hydrogen ion, means proton. Second product is 4F minus fluoride ion plus O2. O2 is gas. Now X2 means halogen gas. X2 plus H2O, second reaction I am talking about. X2 plus H2O, it gives 2 product, HX plus HOX minus HOX, not minus, HOX. HX plus HOX. HX means just like HCl, HBr, HI, halide ion, you can tell. One product. Other product is HOX, hypohalous acid. HOX, X may be chloride, bromide, iodide. HOX. It is called hypohalous acid. Then X2 plus H2O, it is giving HX plus HOX, where X is chloride or bromide, or chlorine or bromine. Now, one more reaction I am telling you, that 4I plus 4H, iodide, I am talking about the reaction of iodine. 4I plus 4H plus means aqueous solution, acid you can tell, plus O2. These 3 will react and it will give 2I2. 4I was there, that's why now you are getting 2I2 solid you will get, plus 2H2O, water. Means 4I plus 4H plus. 4H plus means acid plus O2. It gives 2 product, 2I2. I2 means here solid plus 2H2O. This I told some reaction. Now, anomalous behavior of fluorine. Question is asked. Many question is asked. Listen carefully. Like other elements of P block present in second period of the periodic table, fluorine is anomalous in many properties. For example, ionization enthalpy electronegativity and electron potentials are all higher for fluorine than expected from the trends set by other halogens. Also, ionic and covalent ready, melting point and boiling point, enthalpy of bond dissociation and electron gain enthalpy are quite lower than expected. Again you listen. Ionic and covalent ready, melting point and boiling point, enthalpy of bond dissociation and electron gain enthalpy are quite lower than expected. The anomalous behavior of fluorine is due to its small size. First reason I am telling why it is showing anomalous behavior. Then its first reason is a small size. Second reason is highest electronegativity. Third reason is low FF bond dissociation enthalpy. Fluorine FF bond is low dissociation enthalpy, bond dissociation enthalpy. And next reason is non-availability of d orbitals in valence shell. Non-availability of d orbitals in valence shell. These are the, you can say, reason why it is showing anomalous behavior. Most of the reactions of fluorine are exothermic, means it will release energy, heat. Most of the reactions of fluorine are exothermic due to a small and a strong bond formed by it with other elements. Most of the reaction of fluorine are exothermic. Why? Because, or you can tell, due to the small and a strong bond formed. A small bond means a strong bond. A small bond means a strong bond. Correct? Then due to the small and a strong bond formed by it with other elements, it forms only one oxoacid. This question is asked. Fluorine forms only one oxoacids, while other halogens form a number of oxoacids. Hydrogen fluoride is a liquid. Hydrogen fluoride HF is a liquid. Boiling point 293 Kelvin. This is due to a strong hydrogen bonding. Other hydrogen halides are gases. This I have discussed about anomalous behavior of fluorine. Now other reaction I am telling you. Reactivity towards hydrogen. This reactivity towards hydrogen, I am talking about halogen in general. They all react with hydrogen. All halogen react with hydrogen to give hydrogen halide. But affinity for hydrogen decreases from fluorine to iodine. Means highest is with fluorine and lowest is with iodine. Hydrogen halides dissolves in water to form hydrohalic acids. Hydrogen halides dissolves in water to form hydrohalic acids. I will tell some properties of this halide. The acidic strength of these acids, means halide I am talking about, halogen halide. The acidic strength of these acids varies in the order. HF is less, hydrofluoride is less than HCl, HCl is less than HBr, HBr is less than HI. This is the acidic strength. Acidic strength of these acids means hydrogen halide I am talking about varies in which order? Then HF is less than HCl. Hydrogen fluoride is, it means weakest, you can tell, weakest. HF is less than HCl. HCl is less than HBr. HBr is less than HI. HI is highest HI has highest acidic strength and HF has lowest. Okay, HF is less than HCl, HCl is less than HBr, HBr is less than HI. Question is asked. The stability, now I am talking about the stability. The stability of these halides decreases down the group due to decrease in bond dissociation enthalpy. HX bond is there, then bond breaks, then stability of these halides decreases down the group due to decrease in bond dissociation enthalpy. What is the order of stability? Then HF is greater than HCl, HCl is greater than HBr, HBr is greater than HI. What I talked about the acidic strength, reverse of this. Means bond energy stability I am talking about. HF is more stable than HCl, HCl is more stable than HBr, HBr is more stable than HI. This question is also asked. Okay, both are reverse, you remember. Now reactivity towards oxygen. But before going to this reactivity towards oxygen, I want to tell properties of hydrogen halide. After that I will come. Melting point of HF is 190 Kelvin. Melting point of HF. And HCl is 159 and HBr is 185 and HI is 222. Means 190 is HF. After that HCl is less 159 and HBr is 185. Correct? This is more than HCl and HI is highest 222. This is the melting point. Boiling point also will follow same type of trend. Means 293, HF is 293 and HCl is less 189. Melting point was also less than HF. Boiling point is also less than HF and HBr more than HCl 206 and HI is highest 238 Kelvin. Okay, then melting point and boiling point trend is same way. Means HF is more, melting point of HF and boiling point of HF is greater than HCl. HCl is 159 and HCl boiling point is 189. But both melting point and boiling point both are more for HF. HF is more. Melting point and boiling point, this HF is more than HCl. And HBr, HI, then HI is highest. Melting point also, boiling point also. HI is melting point 222 and boiling point 238. And HBr is less than HI. 185 melting point and boiling point 206. Bond length, actually more the bond length, less the dissociation energy. Keep in mind, easily it can be broken. If bond length is more, it will break easily, means bond energy will be less. Then bond length is for HF 91.7 91.7, HCl 127.4, HBr 141.4, and HI 160.9. That's why HF is weak acid, because it will not release H quickly because bond is strong. This is the reason. And HCl is more, HBr is further more, and HI is highest, 160. That's why HI is the strongest acid in halide. Only in halide HI is the highest and HF is the weakest. And bond dissociation energy, actually this length what I told you in picometer. Bond length is in picometer. What I told you, 91.7 for HF, 127.4 for HCl, 141.4 for HBr, and 160.9 for HI. Now bond dissociation energy. Dissociation energy now I am talking about. That was the bond length in picometer. Now dissociation energy in kilojoule per mole. Then this is the 574 for HF, highest. It is the highest because it is bond is strong. That's why its a bond energy is, dissociation energy is highest, 574. HCl is 432, less. HBr is 363, further less. HI is 295, further less. Okay. And pKa value, Ka value you know, that is the dissociation constant of acid. By Ka value you can tell bond is this thing. Ka value will tell about this which acid is strong or weak. If Ka value is more, means acid is strong, and reverse same way for Kb value, base, which is more basic. If Kb value is more, then you can tell the substance is more basic. B means base. Okay, dissociation constant of acid, that is called Ka. Dissociation constant of base, that is called Kb. Then here we are talking about acid. Then here pKa, P is the P term is associated. Then just like a pH is equal to negative logarithm of hydrogen ion concentration. Same way it is a pKa, with the Ka potent P is used. Okay. Then now it is called pKa. Ka value in term of P you are talking about. Then pKa value for HF is 3.2. Actually more the pKa value, less the acidic. Okay, if a pKa value is more comparatively, then acid will be weak. Then now you can see pKa value for HF. HF, you know, it is the weak acid in comparison to HCl, HBr and HI. Then now HF value is, pKa value for HF is 3.2, but others are in negative. That's why HF value is weak acid, 3.2 plus 3.2. HCl is minus 7.0 and HBr is minus 9.5, more negative, because HBr is stronger acid than HCl, and HI is minus 10.0, highest, strongest acid. That's why value is more negative, minus 10.0. Again I am telling plus 3.2 because HF is a weak acid. HCl is more acid than HF, that value is minus 7.0. HBr is minus 9.5, more negative, and HR is highest, minus 10.0. Okay. This question is also asked. They will give the value. You have to find out pK value they will give. Ka value Ka value and pK value is inversely related. Okay. If generally K value is more, means acid is more stronger. But here if pK value is there, then reverse case. Reverse. Okay. Then pK means more the value, less the weak the acid. Okay. Don't confuse with Ka and pK value. What is the Ka value is more, then more acidic. But if pK is there, pK in term of pK, then if pK value is more, then acid is strength. Acid strength is less weak. Now I am coming towards the other reaction. Reactivity towards oxygen. Halogen reactivity towards oxygen. Halogens form many oxides with oxygen, but most of them are unstable. Fluorine forms two oxides, OF2 and O2F2. Remember it. Question is asked. Fluorine forms two oxides, OF2 and O2F2. However, only OF2 is thermally stable at 298 Kelvin. These oxides are essentially oxygen fluorides. How will you tell OF2? Then what is the name? How will you tell OF2? What is that? How will you tell? Just like you are telling sodium chloride, potassium chloride. Then if OF2 is there, then how will you name? Then essentially oxygen fluoride. It is called oxygen fluoride. First oxygen, then fluoride. NaCl, sodium chloride. First you are taking sodium and then chloride. Means negative, electronegative element is telling a letter. First you are telling electropositive. Then you are telling electronegative. Na plus Cl minus, sodium chloride. Then sodium is electropositive, chloride is electronegative. Same way, here oxygen and fluorine, both are electronegative. But fluorine is most electronegative. If you will compare, then fluorine is more electronegative than oxygen, despite both are negative. That's why it is named as oxygen fluoride. Oxygen fluoride, OF2. Oxygen difluoride you can tell, or O2F2 you can tell simple oxygen fluoride, or dioxygen difluoride. Both way you can tell. Okay. Then this how it is just named, I have told you, because oxygen is comparatively less electronegative than fluorine. That's why it is called oxygen fluoride, because of the higher electronegativity of fluorine than oxygen. And both fluorides, oxygen fluoride I am talking about, both are a strong you can say this fluorinating, you can tell. Both are a strong fluorinating agents. O2F2 oxides, O2F2, actually a special properties I am telling you. O2F2 oxidizes plutonium. O2F2 oxidizes plutonium to PuF6. Plutonium will convert to plutonium fluoride, PuF6. Question is asked. And the reaction is used in removing plutonium as PuF6 from a spent nuclear fuel. This reaction is very, very important. Question is asked. In a nuclear thermal plant, this reaction takes place to remove the plutonium, because fluorine will react with plutonium and it will form PuF6. Okay. This reaction is very, very important and asked in examination. Then this I have told you, this reaction means plutonium O2 F2 oxidizes plutonium to PuF6, and the reaction is used in removing plutonium as PuF6 from spent nuclear fuel. Now come to the chlorine. Chlorine, bromine and iodine. Chlorine, bromine and iodine form oxides in which the oxidation states of these halogens range from +1 to +7. Again you listen. Chlorine, bromine and iodine form oxides in which the oxidation state of these halogens ranges from +1 to +7. Means maybe +1, +2, +3, +4, +5, +6, +7. A combination of kinetic and thermodynamic factors lead to the generally decreasing order of stability of oxides formed by halogens. Then what are the order of stability of oxides? Then iodide is stronger than chloride. Chloride is stronger than bromide. This is the order, decreasing order. Iodide is more stable. Oxides I am talking about. Okay, oxides of iodine is stronger than iodide of chloride, and iodide of chloride is stronger than this oxides of bromide. Means I is greater than chloride, chloride is greater than bromide. I am talking about the oxides. Okay, oxides of iodine, oxides of chlorine, oxides of bromine. Then oxides of iodine is stronger than chloride, and chloride is stronger than bromide. The higher oxides of halogen, higher oxides, maybe +3, +4, +5, +6, +7, higher. The higher oxides of halogen tend to more stable than lower one. This question is also asked. Higher oxides, the higher oxides of halogens tend to be more stable than lower ones. Now chlorine oxides, different type of chlorine oxides I am telling you, question is asked. From this chapter many question is asked. Then chlorine oxide, as for example Cl2O, other oxide is ClO2, third oxide is Cl2O6, and fourth oxide is Cl2O7, are highly reactive oxidizing agents and tend to explode. These are explosive also, tend to explode. Again I am telling Cl2O, first oxide, ClO2, second oxide, Cl2O6, third oxide, and Cl2O7, fourth oxide, and all are highly reactive oxidizing agents and tend to explode. Okay. ClO2 is used as a bleaching agent. Again here important question. ClO2 is used as a bleaching agent for paper pulp and textiles and in water treatment. Remember, this question is very, very important. ClO2, 4 oxides I told you that ClO2, second one. ClO2 is used as a bleaching agent for paper pulp and textiles and in water treatment. Now come to the bromine oxide. There are 3 oxides of bromine. Br2O, first, second is BrO2, third BrO3, and all 3 are the least stable. Question is asked in comparison to chlorine oxides, bromine oxides are weaker. Okay, Br2O, BrO2, BrO3 are the least stable halogen oxides. You can say middle row anomaly, and exist only at low temperature. You will find BrO2, BrO3 and Br2O first, BrO2, Br2O first, second is BrO2, third is BrO3 are least stable and exist only at low temperature. They are very powerful oxidizing agent. Now come to the iodine oxides. Then iodine oxide, again there are three. I2O4. First is I2O4. Second is I2O5. Third is I2O7. And all three are insoluble solids. Iodine is heavy, you know. That's why oxides are also heavy, solid, and are insoluble solids. Okay, the iodine oxides are insoluble solids and decomposes. It will decompose on heating. I2O5 is very good oxidizing agent. Remember, I2O5 iodine pentaoxide is a very good oxidizing agent and is used in estimation of carbon monoxide. This question is asked. I2O5 means iodine pentaoxide is very good oxidizing agent and is used in the estimation of carbon monoxide. Now next chemical reaction I am talking about, third one, that is the reaction towards metal. Actually I have discussed two chemical reaction, reactivity towards hydrogen. Okay, and after that I have discussed that reactivity towards oxygen, and third now I am going to discuss reactivity towards metal, means halogen reactivity towards metal. Halogen react with metals to form metal halide. For example, bromine react with magnesium to give magnesium bromide. Mg plus Br2, Mg is a solid. Then Mg plus Br2, it will give MgBr2. MgBr2 is also solid and Br2 is liquid. Okay, reddish liquid. The ionic character of the halides, decreases in the order, which order? Then this metal fluoride I am talking about. Metal fluoride is greater than MCl, means metal chloride, and MCl is greater than MBr, metal bromide, and metal bromide is greater than metal iodide. This is the ionic character. I am telling, ionic character of the halides decreases in the order of, means MF, metal fluoride is have more character than MCl. MCl is more character than MBr. MBr is more character than MI, where M is a monovalent metal. This question is also asked. Okay, ionic character. Then ionic character decreases in the order of MF is highest. Ionic character in metal fluoride is highest. After that, second is MCl, third is MBr, and fourth is Mi, where M is a monovalent metal. If a metal exhibits more than one oxidation state, then the halides in higher oxidation state will be more covalent. This question is also asked. The halides in higher oxidation state will be more covalent than the one in a lower oxidation state. For example, see example I am telling you, all questions are asked in all examination. Okay. Then for example I am telling you SnCl4, PbCl4, antimony Cl5 and UF6, uranium hexafluoride, UF6 are more covalent than SnCl2. SnCl2, it has less oxidation state, only +2, but SnCl4 +4, PbCl4 +4, SbCl5 +5, means all metal have +5 oxidation state. UF6, U has +6, that's why they are more covalent than SnCl2, PbCl2, SbCl3, UF4 respectively, where Sn is only +2, Pb +2, SbCl3 +3, UF4 +4. Okay, then this higher oxidation state are more covalent than lower oxidation state. Now next properties I am talking about halogen reactivity of you can say towards the halogen. Now very good reaction, that reactivity of halogens towards other halogens, means halogen they themselves will react. Halogen they themselves will react. Why they will react? Then now already I discussed, because fluorine is more reactive than chlorine. Chlorine is more most electronegative, you can tell, most electronegative, or more electronegative than chlorine. Chlorine is more electronegative than bromine. Bromine is more electronegative than iodine. Then higher electronegativity will be work as a electronegative, and less electronegative will behave as a positive, electropositive, like that. Less will behave as electropositive, more will behave as a electronegative. Means just like two rich persons are there, then one is more richer than other. Both are rich, but one is this less in comparison to both. One is more richer than other, but in general both are richer person. Then one will behave as electronegative, other will behave as a electropositive. Then electropositive, electronegative, both will combine and it will form a molecule. This is the reason why halogen react they themselves. Means more electronegative will behave as a electronegative, and less electronegative will behave as a electropositive. Then I am discussing little more. Halogens combine amongst themselves to form a number of compounds known as interhalogen compounds or interhalogen molecules. They form number of compounds known as interhalogens of the type XX dash, XX dash, X and X dash 3, X and X dash 5, and X dash 7, where X is a larger size halogen, and X dash is a smaller size halogen according to the size. Then X is a larger size halogen, and X dash is a smaller size halogen. Now one question I am telling you which is asked in examination. Fluorine exhibits only -1 oxidation state, whereas other halogens exhibit +1, plus 3, plus 5 and plus 7 oxidation state also. Why? Explain it. Question is asked. why fluorine shows only -1? Other shows +1, +3, +5 and +7 oxidation state. Why? Then explanation I am telling you. Fluorine is the most electronegative element and cannot exhibit any positive oxidation state. Fluorine is the first size is small and is the electronegative element and cannot be exhibit any positive oxidation state. Okay. Other halogens have d orbitals. Fluorine has no d orbitals, but other halogens have d orbitals and therefore can expand their octet and show +1, +3, +5 and +7 oxidation states also. Correct? Fluorine is the most electronegative element. It is small in size and has no d orbital and cannot exhibit any positive oxidation state because it can't release any electron. Only it can take because it is most electronegative element. It wants electron. But other halogens have d orbitals and size is comparatively bigger and therefore can expand their octet because d orbitals are back and d orbitals are there. Then they have d orbitals and therefore can expand their octet and so +1, +3, +5 and +7 oxidation state also. This I have discussed. Now I am stopping only here. Next class I will discuss chlorine. Okay, chlorine, that properties, this preparation properties and this uses I will discuss in the next class. Thank you.